Hello everyone and welcome to our little intro on pKa and pH. So at this point we may or may not have talked about pKa a little bit, but we're going to talk more about the finer details, sort of where it comes from, and we're also going to talk about pH, which you may have seen in Gen Chem, depending on your background. It may have been a while. So we're just going to review the things we need to know so that we can move on to the next section. So pKa is actually just a formula. So pKa means it's the negative log of the Ka value. So whatever that number is, you can just take the negative log of that value. So now the question is, what is Ka? Ka is an equilibrium constant of a reaction that's doing something called the acid reaction. This is the Ka reaction or the acid reaction for HCl. HCl plus water gives the conjugate base, which is Cl minus plus H3O plus. It's how likely is that H plus to come off and make it onto the water. So now I put the formula for KEQ up here. KEQ equals the concentration of the products over the concentration of the reactants. Concentration is shown by these brackets here. So if I was going to draw the KEQ for this equation, it would look like this. Notice first that as I've written the equation, I wrote Ka. That's because, like I said, you can call it KEQ, but because it's of the specific acid reaction, we're calling it Ka. So Ka equals concentration of chlorine minus concentration of H3O plus. Those are multiplied over the concentration of HCl. One thing I left off was the water, and that's because whenever we do the KEQ, that actually doesn't show up. Anything that's a pure liquid or pure solid is not included, and the reason is because they can't change concentration. The concentration of a pure liquid is going to be 1, which means it wouldn't show up in the equation. So if you look below, the Ka value is given. This number is 1.3 times 10 to the 6th. That's a really big number. That says that because the Ka is so much bigger than 1, that there are far, far more products than there are reactants. Because remember, Ka is just KEQ, which is products over reactants. So because that's the case, we know HCl is a very strong acid. But also, do we really want to be talking about 10 to the 6th and 10 to the minus 6th? Those numbers are really big. So if we use the log, we can see that that pKa would just be negative 6.1. That's a much easier number to work with. Now, as I've said, in organic, we're not going to use a whole lot of math, so I'm not going to ask you to calculate these numbers. But if you want to get an idea, you can use an estimate, so I'll show you how to do that. So the way that you can estimate the pKa is to look at the exponent of the scientific notation. So here where it says times 10 to the 6th, I'm talking about the 6th. So I take that 6, and that's going to be my number, and then I'm just going to take the negative of that exponent. So it would be negative 6 is about the pKa. So you're able to estimate it. You can also, of course, go the other way. So if you know the pKa, for example, the pKa of this molecule is about 4. So then I can also figure out the equilibrium constant. So if the pKa is about 4, that means that the equilibrium constant would be Ka equals 10 to the what? Right, negative 4, because you have to switch it to the negative. And then that gives you an idea of about how much product there is compared to the reactants. Like we said before, the Ka comes from the acid reaction for a specific reaction. That means that not only will the reaction be different, but that the Ka number should be different for different kinds of acids. So every acid has its own specific pKa and Ka values. And we saw that on our chart for the sum pKa's to know. They're all a little bit different. Some of them are similar, so there's a trend, which is good, but they're not identical. So what information can we get from the pKa? So first of all, we know that a lower pKa means that it's actually more acidic. Remember, HCl was negative. That's actually a really strong acid, right? So that means that low pKa's are strong acids and high pKa's are weak acids. So lower pKa makes a stronger acid. This also means that the H3O plus concentration should be high if you have a strong acid. So there should be a lot of products in H3O plus if you have a strong acid, which is a low pKa. For this example here, we can estimate the Ka, so we're going the opposite direction. If we were going to estimate the Ka, we would take the pKa and just make that 10 to the negative exponents. So the pKa for HF would actually be 10 to the negative 3.2, which is about 0.001, right? Because that would be 10 to the negative third. For HBr, it says -9 for the pKa, so what would be that Ka value? That's right, it would be 10 to the 9th. So obviously, one of these is a stronger acid. Which one is it? Right, it's HBr. Which of these solutions would have more H3O+? Right, it's going to be HBr again because that forms more products because it has the lower pKa. So what about pH? So far we've been talking about pKa's, which are related to specific molecules. Now we're going to talk about pH, which is usually more about the solution around a particular molecule. So if we're going to talk about solutions, especially those that are in your body, we're going to need to talk about water, and that's what pH is related to. The first thing that we know is that water is amphoteric. That means it can be either an acid or a base. It can do either job. If you look at the chemical equation shown below, you see water twice on the side, but actually each of these waters is acting a little bit differently. So for this equation, the water plus water, equilibrium arrow, because it's in equilibrium, forms H3O plus OH minus. We want to know the conjugate base and the conjugate acid. Obviously, normally we would start by labeling the acid and the base, but in this case, they're the same. So we can just label either one of these as acid and either one of these as base. So now, based on what we know about conjugate acids and conjugate bases, try to label the conjugate base and conjugate acid for this equation. Pause the video while you do this. Alright, so hopefully this is what you got. The conjugate acid is going to be this one because it's got a positive charge, and the conjugate base is going to be this one because it has a negative charge. So similar to how we had the thing Ka, which was a KEQ for a specific reaction, we also have Kw, which is also a KEQ for a specific reaction. And the reaction is the one we just did. It's water plus water, equilibrium arrow, makes H3O plus and OH minus. So in normal water, this is constantly happening. There's an equilibrium between ions and actual just regular water. So the KEQ is just equal to Kw. By definition, Kw is equal to the concentration of just the products, because remember, we're not using those reactants because they're pure liquids. And then that value is equal to 1.0 times 10 to the negative 14th. This number is interesting because it shows you the relationship between H3O plus and OH minus, but we're not going to go into a lot of math about it in this course. So that's all fine and good, but we now need to talk about how it relates to the pH scale. The pH scale is probably the most popular way of talking about this. People talk about pH in places much outside of science, so it's actually pretty common. I'm sure that your family even knows what pH is. If you were to mention it, they would have some idea what you're talking about. So the pH scale is actually related to what we were just talking about. So here's the equation. As you can see, pH is equal to the negative log of the H3O plus concentration in a solution. So just like pKa before, we can figure this out using our calculator, or we can estimate using the exponent. So if I were to take H3O plus equals 10 to the negative 7th, what pH would that be? Well, if we estimate, we can see right away that the exponent is 7, so we're just going to make that negative 7, negative times a negative, so then that would be positive 7. So the pH would be 7. And so like I said, we're not going to do a lot of math, but it's nice to be able to estimate and go between the concentration of H3O plus and the pH, and the same thing with the Ka and the pKa. Let's do an example. So here it says a solution of HCl has a concentration of H3O plus that's equal to 0.010 molarity. What is the pH? Often we'll have a number that's in scientific notation for the concentration here, but in this case we don't, so I would first start by putting that into scientific notation. Hopefully we all know how to do that, so pause the video and do that first. So here's what we got. So then once we have that, then we can just take the exponent, because this is just equal to 1, and figure out what is the pH. That's right, the pH should be equal to 2. So is this solution acidic or basic? Now is a good time to have a quick reminder of what the scale is. So when you're looking at the pH scale, neutral is 7 because it's 10 to the minus 7th for both the concentration of H3O plus and the concentration of OH minus. That's what makes it equal. So neutral, pH 7. Then if you have a pH that's below that, that's going to be 10 to the minus 3rd, 10 to the minus 2nd of H3O plus concentration. That's very acidic, so that's where the acids are. So anything lower than pH 7. Anything above pH 7 are going to be our bases. That's where the concentration of H3O plus is going to be much smaller, like 10 to the minus 8th, 10 to the minus 12. That's a very small amount of H3O plus. So that's not an acidic solution, that's a basic solution. So bases will be anything above that pH 7. So using these numbers, we can easily identify if a solution is acidic, basic, or neutral. So now that we've got a little bit more foundational knowledge about pH and pKa's, we're going to use the pH and pKa's to predict what form a molecule will be in depending on the pH of the environment. Then from there, we can talk about the effects of pH on drug chemistry and how drugs work in your body. So in that case, we'll be able to tie all the knowledge we've learned about acids and bases together into a really interesting biological example. Hopefully that will be fun.